Hi, I'm Mudinda and I'm here to help you understand maths better for free. Well, matriculants, today I want us to talk about divergent versus convergent geometric series, as well as the sum to infinity. Now, if you've made it this far in the playlist, congratulations! You're almost done with everything you need to know for sequences and series, and then in the next video, we're going to be looking at exam past papers. Now, imagine if you had this sequence here, this green sequence here, and we wanted you to determine the sum of the first two terms, the sum of the first 5 terms, sum of the first 10 terms, and the sum of the first 20 terms. As you can see, we're multiplying by 3 to get to the next term each time. Therefore, this is a geometric sequence or geometric series. R, the constant ratio, 6 over 2, which is 3. And A, the first term, is 2. Now we know that the sum of the first n terms of a geometric sequence is a into r to the n minus 1, all divided by r minus 1. So the sum of the first two terms, for example, would be 2 into 3 to the power of 2 minus 1, all divided by 3 minus 1. Now that should give you 8. But you can also just manually find the sum of the first two terms by adding 6 and 2. Now, if you change this 2 to a 5, then you'd find the sum of the first 5 terms. 2 to the power of 3 times 5 minus 1, all divided by 3 minus 1. And that would give you 242. Let's find the sum of the first 10 terms. You should get 59,048. And the sum of the first 20 terms. As you can see, the more terms we add, this number just gets bigger and bigger, which makes sense intuitively. The more of these terms we're adding, the bigger and bigger this should become. The sum of the first 20 terms would be 400 and I'm Jacob Zoomering this number. 3,486,784,400. That's the sum of the first 20 terms. So as you can see here in this green sequence, the more terms we add, the number just gets bigger and bigger. But when you have this kind of sequence, surprisingly, it doesn't get bigger and bigger. See, here, we're multiplying by a half in each term. So the constant ratio r is 1 over 2. The first term a is 1 over 2 as well. Sum of n would be a into r to the n minus 1, all divided by r minus 1. So the sum of the first two terms, for example, would be the first term, which is 0,5 or a half, and 0,5 to the power of 2 minus 1, all divided by 0,5 minus 1. So it's adding a quarter and a half, and that would give you 3/4. What about the sum of the first 5 terms? Well, that should give you about 31 over 32 if you press it in your calculator, which is 0,969. And the sum of the first 10 terms would give you 1023 over 1024. Now this is about 0,999. Yes, it's increasing, but it's weirdly increasing by very little, given that we added a whole 5 other terms. It's from this 5, it's increasing by very little. And look what happens when we find S20. You get 0,9999999. And if you put in place of n 50, the sum of the first 50 terms is 1. If you try to find the sum of the first 100 terms, it's also 1. Okay, so there's a difference between the green sequence here and the blue sequence here. They behave differently. The more terms we add on this green sequence, the bigger the sum just is. It just gets astronomically bigger. We call this kind of a series a divergent series. Why? Well, it diverges to infinity. It just keeps getting bigger up until infinity. But we call this blue sequence a convergent series. Convergent series. Why? It converges towards this particular number. In our case, it converges to 1. Won't always be 1. Some series converge to different numbers. But a convergent series, we can see as we add more and more terms, it just gets closer to a particular number. Unlike a divergent series, it just gets closer to infinity. It just gets bigger and bigger. Now, without doing all this manual work, we can know whether a series will be convergent or divergent. You might have noticed by now that maybe there's something to do with r. The fact that here r is a fraction, sorry, that's a, r is a fraction, and the fact that here r is a whole number, and it definitely has something to do with that. Here's the summary. Whenever r is a whole number, like if it's bigger than 1, okay, it doesn't have to be a whole number. As long as it's bigger than 1 or less than -1, then the series will be divergent, okay? The sum of that series gets bigger and bigger. It diverges to infinity. But if r is a fraction, in other words, if it's between -1 and 1, then that series is convergent. The sum of that series converges towards a specific number, like this one that converged towards 1. The more sums we add, the closer and closer the sum got to 1. Great. Now let's talk about the sum to infinity of a geometric series. In maths, we really believe in infinity. And we want to find out how can we get the sum of as infinitely many terms as possible in a sequence. Well, we can get that if it's geometric by just taking the first term and dividing that by 1 minus r. That gives you what we call the sum to infinity. So for example, if you have this here r would be term 2 divided by term 1, which is a ninth divided by a third. That's like 1 over 9 times 3 over 1. 3 into 3 is 1, 3 into 9 is 3. So r here is 1 over 3. We're multiplying by 1 over 3 to get to the next term. Okay. A is a third. The sum to infinity for this, which is always a over 1 minus r, would be 1 over 3 divided by 1 minus 1 over 3. Now, if you put that in your calculator, 1 over 3 over 1 minus 1 over 3 should give you a half. So the sum to infinity here is a half. Have a look at this example. Here we're told that the sum to infinity of a series is 400, and its constant ratio is a half, and we're asked to determine the first term. Well, remember, the formula says the sum to infinity is always a over 1 minus r. So in place of sum to infinity, we can put 400, since we've been told that the sum to infinity is 400. And we don't know the first term, but we know that r is a half. So if you cross multiply, so we have here 400 is equal to a over a half. If you cross multiply here, since we have two fractions separated by an equal sign, you would get that therefore a is just 400 times a half, right? Which means that therefore a is 200. So sometimes they could give you the sum to infinity and not give you a, and maybe give you just r and sum to infinity. Or maybe they could give you sum to infinity and a and ask you to find r. Okay. Now, matriculants, this question says the sum to infinity of a geometric series with positive terms is 25 over 6, and the sum to infinity and the sum of the first two terms is 8 over 3. Find a, the first term, and r, the constant ratio. Feel free to pause the video and try, because we've actually done questions like these. This is where one statement, i.e. this blue one, needs to give you an equation that has two unknowns, and the other statement, the red one, needs to give you another equation with two unknowns, and you can solve simultaneously, much like we did when we looked at complex sequence and series questions. Now, let's do this together. I actually want to start off with the red part that tells us that the sum of the first two terms is 8 over 3. So term 1 plus term 2 is 8 over 3, right? Now term 1 is a, and in a geometric sequence, term 2 is a times r, right? Now I can make a subject of the formula if I just take a as a common factor here. In brackets, I'll have 1 plus r. Then I can divide here both sides of this equation by 1 plus r, right? Divide by 1 plus r, so that the 1 plus r can disappear here, and I'm left with a is equal to 8 over 3 divided by 1 plus r, which is 8 over 3 multiplied by 1 over 1 plus r if you tip and times. Now, in other words, you end up here with a being 8 over 3 into 1 plus r. And I actually just want to leave this here and let me call it equation 1. Now, the second part, the blue part, tells us that the sum to infinity is 25 over 6. Now, we know that the sum to infinity is always a over 1 minus r. So a over 1 minus r is equal to 25 over 6. If you cross multiply here, you get that 6a is equal to 25 times 1 minus r. Let's call this equation 2. And how about substituting equation 1 into equation 2? Meaning, wherever I see a, I'm going to put 8 over 3 into 1 plus r. So now I have 6 multiplying 8 over 3 into 1 plus r is equal to 25 into 1 minus r. Now, if you just have a look here, we have 6 and 3 in the denominator. 3 goes into 3 once, 3 goes into 6 twice. Okay, so what we end up having here is 2 times 8, which is 16 over 1 plus r, is equal to 25 times 1 minus r over 1. Since we have two fractions separated by an equal sign, I can cross multiply there. Now 16 times 1 will be 16. Then on the other side, I'll have 25 into 1 minus r multiplying 1 plus r. Now you know that when you have this, like the same terms but a plus and a minus, it's just 1 minus r squared if you simplify it. So essentially, what you have here is 16 is equal to 25 minus 25r squared. So if I put 25r squared on this side I'll have 25 minus 16. So 25r squared is equal to 9. Okay, and if I divide both sides by 25, then r squared will be 9 over 25. And that's going to therefore mean that r is either plus or minus the square root of 9 over 25. Now the question is r positive? So r can either be positive 3 over 5 or r can be negative 3 over 5. But the only way a sequence can have positive terms is if r is positive. So the correct answer is this one, the positive version. If a sequence has a negative r, like for example, imagine the first term was 3 and the constant ratio was negative 2. The next term would be minus 6, right? Because 3 times negative 2 is minus 6. Now negative 6 times negative 2 would be positive 12. Positive 12 times negative 2 would be negative 24. As soon as you have negative r, you alternate between positive and negative values. So we can't say that this one, well, apart from that, but because they said this has positive terms only, we must make sure that we pick the one with an r that is positive. Now, because we found r, we can easily find a. We know that a, what did we say about a? We said a is always equal to 8 over 3 into 1 plus r. Which means it's 8 over 3 into 1 plus 3 over 5. If you put all of this in your calculator, you should get that therefore a is 5 over 3. Great, my chicklets, that's the sum to infinity, and in the next video we're going to just be purely looking at past paper examples from the 2020